dips. Voltage dips probably in the 60% range when equipment's starting up out there. So. And extends equipment life and reducing maintenance costs. Well, that's kind of a catchphrase, but that's only if it's properly implemented with filtering and you've addressed power quality issues. Without those items addressed, maintenance for VFD motors can be pretty high, real high. And we'll have those answered here before this session ends. So, inrush current, when you go from across the line start motors to either soft starts or variable speed drives, not a really big difference because the drive will do soft starts. Only difference is the soft start can't change the speed of the motor. But preventing that inrush current will prevent voltage dips. So, this was a job I was called out on. They were losing drives, motors. Anybody recognize a problem with this installation? As you can probably see from the dark spots here, these old drives got replaced with new drives. This room had 52 drives inside this room. This room, not a main electric room, but an electric room. And the drives were installed in this electric room. This was a food processing facility, and everything out in the processing facility is stainless steel. Well, I can't imagine what a stainless steel drive would cost, but because of first cost, they stick the drives, and they were always in here, so they just stuck them and left them here. The motors are somewhere between 400 and 500 feet away. So, losing motors and losing drives. And this was a facility, this is Ocean Spray bottling facility in Las Vegas. They bottle about 1 million bottles of various juices, from apple juice to cranberry juice, almost a day. And so I get a call from this outfit. I said, well, how old is your building? Oh, it was built in the 70s, 80s. I said, you have any drives? Yeah. You got a generator? Yeah. I said, you got a grounding problem? How do you know? You haven't seen the building. I said, well, based on what you've described to me, it says, I've been an electrician for 50 years. I said, we don't ground our buildings for this type of technology. So you got a grounding problem. I said, I'll tell you what, I'll come and I'll look at it. So they take me to this electric room, and I look and I said, oh, there's your problem. Anybody see an issue?
The gutter looks illegal to me.
Huh?
The gutter.
What's the problem?
With the 30 current carrying conductors in the gutter, right?
What's that?
30 current carrying conductors going across the field gutter.
I'm sure you guys are probably not aware of the standard installation practices for variable speed drive. Do you recognize it?
Mine looks being separate.
How about you? You recognize the problem?
Mixed in the
I'm
same
right off
gutter.
that.
Okay, standard practice for installing drives, right?
Oh, there's only one in, one out.
The innie and the outie, I so told them, your innie and your outie is the same conduit. What are you talking about?
Gutter. It's all mixed together.
I said, your innie is 60 hertz, your outie is probably somewhere around 10,000 hertz. They cannot be in the same conduit, and they can't be in the same gutter. What are you talking about? I said, well, the magnetic field around that 10,000 hertz is going to influence the 60 hertz, and the whole thing is just going to, can't work. And it's just,
It's like a heater.
you know, and to travel that far, and your motor's 400 and 500 feet away, and you're using building wire, what are we going to do? I said, well, based on what I'm seeing here, you had an electrical contractor, I'm assuming, put these new drives in. I says, whoever he was, I said, you probably better take him out in the desert and bury him. Because his electrical contractor should not install drives like that. I said, you're gonna have to re-pipe all of this and pull VFD wire out to those motors and put filtering on to correct the problem. So anyway, I like this picture because it's probably the worst installation I've seen in our industry. And I'm gonna have to guess it was probably a non-union contractor because they've never been, they don't go through an apprenticeship program. They don't go through a training program like we have. And therefore, we wouldn't install it that way because we know better. Right? And if you do install it that way, then don't expect it to work. It will not work, can't work. Absolutely cannot work. Because it's like putting a transmission line inside of a 120 volt conduit. You know, you're on a piece of equipment, a variable speed, a variable air volume box that controls the amount of air that flows in this room. Got a microprocessor in there. I gotta get 120 to that motor, and I gotta get a control wire to the motor. I'm just gonna stick in the same conduit. Well, that microprocessor won't even know who's talking to it, because the magnetic field coming off 120 is going to impart signals onto the control cable, and so you can't even run control cable over the top of these fluorescent fixtures. If I had to run to that box and my controller was sitting right up here above the monitor, I could not run that control cable perpendicular across these fixtures because the frequency coming off those fixtures. I have to run it this way, at least a foot away from any energized conductor. At least a foot. So if you're ever in the world of controls, you just need to know that control cable cannot be within 12 inches of power carrying conductors. So, here's another facility, Washoe County, and as you can see, a proper installation. The input, all in single conduit, the output's going to each individual motor. Proper installation. Still having problems though. So basically, your innie is AC. A drive is basically, there's three sections in a drive. You got your innie, your 60 hertz. You've got the center section, I call it, which is the DC section. And then you've got the output section, which I call the transmission side because of the frequency of the drive. It can be anywhere from probably, they're lowering it down to about 4,000 hertz, I think now, up to 20,000 hertz based on manufacturer. So to me, that's transmission speed. I mean, if 15,000 and lower is RFI, radio frequency, and 15,000 above is EMI, electromagnetic interference. So you're in the transmission zone here. And the output, basically, we'll go through all of this, is not a sine wave. It's a square wave. If you have any questions, fire them out there. So here's a simple diagram of what's inside of a variable speed drive. Our AC comes in 60 hertz, and it goes through these bridge rectifiers. Now, a rectifier is either half wave or full wave. So, a single diode, you got a sine wave, right? So, we have, let me set this down where I keep punching buttons. A single diode on each one of these on A phase, B phase, C phase. 2 diodes per phase. So we have a positive diode and we have a negative diode. And its job is to put out an output that looks like this. If I have a half-wave rectifier, only one diode, I'm going to put out an output that looks like this. I'm going to miss the negative section with only one diode. I still put out DC, but the ripple frequency would be tremendous. I'd have to have a gigantic capacitor in here to fill all this gap in, right? A capacitor basically stores energy, voltage, releases energy, right? That's how a capacitor works. So I store all this energy into my capacitor, and when I hit this spot here, the capacitor then drains, right? So I'm draining my capacitor and filling this in, so my output's going to look kind of like this, instead of this big hole here. So the capacitor's going to put out a fairly nice DC signal. The bigger the capacitor, of course, the flatter that DC gets. So that's the purpose of this bridge rectifier. 2 per phase, so I put out I rectify this negative section, and I put out a DC signal on this DC bus, and there's the capacitor to fill in all that empty spot. So the capacitor charges as the voltage builds to here. My voltage builds up, fills up the capacitor. As my voltage drops off, the capacitor discharges and fills in the gap. Make sense? And that's why the weakest link in a VFD is the capacitor, because it's doing all the work. So when drives fail, quite likely it's going to start the failure here, because the more work this capacitor does, the hotter it gets. And as that heat generates, you're either going to get a warning on the drive saying, you know, high temperature or voltage failure. You'll get some kind of a fail because it's got to protect itself. Drive's got to protect itself. Then we get this DC section here, and now we come to what we call the engine part. These are IGBT. That's an integrated gate bipolar transistor. They're a high energy, high amperage transistor. And they work at very high speeds. Because remember, the output of that motor is going to be somewhere between 4,000 and 10,000 hertz. That means these guys are switching at a very high frequency. Very high frequency. And there's where all the trouble occurs. There's all the dirty power going out that motor. And that dirty power goes both directions. So, the more drives you have on a project, the more dirty power you're going to have. And that's where grounding and bonding becomes so severe. So, our input voltage looks like this, and because of this high speed engine, IGBT, it affects the current. And so there's what the current on the input side of the drive looks like. And so this affects the grid being out here. So this current that's now feeding back out on the grid will affect the grid voltage, causing voltage distortion. Because as that current drops, that's one cycle right there. That's one cycle, one half cycle on the positive side. There's the other half of the negative side. So that's one cycle from there to there. So that's happening twice per cycle. So that's 120 times a second. So that generates a lot of dirty power. Drives are the biggest culprit of dirty power. So the output now, we hit the DC section, and the IGBT is switching, and as you can see, an IGBT basically has a very short on, and it starts to develop this component of the sine wave. And then you got a little bit larger on, so the sine wave gets larger. And as this sine wave gets larger and larger, this AC component, or the sine wave component, begins to look like a sine wave. Then on the other side it gets smaller, and therefore it drops down. Smaller and smaller, finally we cross the zero line, and now the negative IGBT starts its action. So 10,000 times these guys are switching. And the controlling factor here is what we call zero crossing. Zero crossing, when the sine wave crosses zero. So I've crossed zero, and this IGBT, the positive IGBT basically, starts to fire. So the positive IGBT starts to fire. So 5,000 times it's making a signal to develop this current sine wave. And now we cross zero here. This guy has to turn off, and the negative guy has to start firing. So now this guy turns off, this guy turns on, and starts to develop this at 10,000 hertz to develop what looks like a sine wave. So that's the basic function of the engine. So you can imagine how critical it monitors that zero crossing to tell which of those guys is supposed to fire. Now we're only looking at one phase. We're only looking at A phase, because B phase is going to happen 120 degrees later. So A phase IGBTs have nothing to do with B phase or C phase, because they're all 120 degrees out of phase with one another. So each one of these guys has a zero crossing 120 degrees apart. But these guys are very critical. This guy has to shut off with it before this guy turns on. Because if they're on at the same time, I'm going to blow something up. These IGBTs will blow up, and I've replaced a lot of them in solar inverters. Same component is in a solar inverter as in a variable speed drive. And I just worked on one this morning out at the Golden Eagle Park. I got the blown up parts in the back of my truck. I had to disassemble this morning to see what was blown, because while I was working on it, the sucker blew up. Oh my gosh. And pretty soon all this black smoke started flowing out of this inverter. Oh crap. Now I got to tear the sucker apart and see what went. But they're 12 years old. They've lived their life. Time. So there's the basic function of variable speed drive. Now remember, this DC bus has to be somewhere around 600 plus volts. How do we get 600 volts off a 40 volt signal? Huh? Anybody remember? How does 480 volts put out 600 volts? Peak, right? What's the peak of 480 volts? We pull out a calculator. Give me the peak. Peak value. Huh?
1.41.
We got a calculator?
683.
Clint's got it over there.
683.
I got a 40 volt signal that I gotta put out 600 volts to feed that bus. 1.414. Remember, RMS .707. RMS will read it from meter. RMS what runs everything. Right? What's peak?
Clint's got it.
Anybody got peak?
683.
683? All right. 683 volts. So, do I have the value I need to provide 600 volts for that DC bus? It has to be plus 600 volts. 600 to 650, depending on the drive, but 600 or greater on that DC bus. Therefore, this 480 volts cannot be less than some value before I do not create this value. So low voltage can cause voltage dips, can cause that DC bus to not reach its maximum. So if I take 600 volts, divide it by 1.414, what's my voltage?
483.
How much?
483. 183.
480?
43.
$600?
And 83. Divided by 1.14.
Went the wrong direction. $680 times .707.
480.76.
That ain't working out right.
I got 40.
Huh?
I got 482, but it's about the same.
42.
The lowest-
You also got 40.
The lowest 480,
480.
so
like
480
482.
times .707. 480 times .707.
Oh, 480.
339.36.
339.
Yep.
0.36.
So if I drop 480 and the power company allows me 10%. So 10% above, 10% below, so 10% would be 480 volts, right? So if I got 480 times 10%, which the power company allows, so I got 5 above, 5 below. So that's 48 volts total, so half that's what, 24. So 480 less 24, am I making sense here? So I got 6, 7, so the lowest voltage, that makes sense there. The power company allows 10% plus or minus. I mean 5 above, 5 below. So 10% of 480 total is 40 volts, right?
So
Right?
it's a split it
10% of 480 is 48, right? 5% would be half of 488, which is 24. So if I take 24 from 480, I got 456, right? So what I'm driving at is the lowest voltage I can provide to a drive is 456 volts in order to produce 600 volts on a DC bus. So to troubleshoot a drive, look at your input voltage, right? It can't be less than 460 volts, say, in order to provide, what's 460 times 1.414?
650.44.
650?
Yeah, .44.
Okay. So, that's an easy troubleshooting tool if you're having problems with the drive. What is my input voltage? Is my input voltage high enough to provide 650 volts to my DC bus? Hope it didn't make it too complicated. Because the secret to success is that DC bus. That DC bus has to be somewhere around 650 volts. And that 650 volts is going to come from the peak of the input voltage.
So I got a question, Carl. What would cause a voltage sag that would last long enough to affect that drive? Because we've all turned on a motor and we've seen the lights dim just a little bit, but they just dim and come right back. Is that long enough?
Good question, because it all depends on the drive manufacturer. What is it capable of riding through?
Mm-hmm.
So it's the ride-through capability of the end use, end device. But the voltage dips we're seeing out there, the USA Parkway, of 65 volts, right? If I can only drop 24 volts, and I'm dropping 65 volts, I'm down to what, 420, 60 volts before 20, so what, 415 volts now. What's 415 volts times 1.414?
586.8.
586, right? So now my DC bus, so now I have an issue where my drive's first thing you're gonna have is gonna trip out on low voltage. And if I had it too long, it could overheat and cause the drive to trip out on overtemp. And I've had to do many times, like I say, the weak link is this guy right here. So that capacitor is trying to fill this guy up to 600 plus volts. And if this happens too long, that poor capacitor is going to say, I'm out of here. And that's what I got in the back of my truck, a bank of blown up capacitors from an inverter. I mean, this capacitor's about that long, about that big around, 5 of them. Any questions so far? Somewhere, oh, there you are. So basically, this is what it all looks like. So there's our distorted current sine wave that's being reflected off of this drive. So there's the start of creating dirty power onto the common bus. The common bus is everything on the switch gear feeding that building. Because once it enters the switch gear from the utility, it's a common bus. The only thing separated is the 120 208 volt transformer. But everything on the 480 volt bus is affected by what starts off from the input side of the drive, creating dirty power. The more drives, the greater effect that has. And now we've got this signal coming off the engine, and it develops an output trying to spin the motor at some speed. So basically what it amounts to is a series of pulses, ons, offs, ons, offs. So simply stated, if I have 50% ons and 50% offs, how fast is my motor going to spin? 50%. So if I'm going to run a 60 cycle motor, I'm going to run it at 60 cycles. Now I can overspeed a motor, somewhere around maybe 5% overspeed, meaning I can run it a little higher than 60 hertz, but depends on the motor. And how slow can I spin a motor? Maybe, depending on the motor, maybe 30%. Because a motor needs cooling. Where does the cooling come from? The fan built inside the motor. So if I don't spin that motor fast enough, the motor can overheat. So there's limits to how low I can spin a motor, and there's limits to how high I can spin a motor, and a VFD can do both. Spin too high, spin too low. So with proper test equipment, most multimeters can measure DC volts as well as AC. So I can check my voltage of my input to find out where my problem is coming from. I can check my DC bus for the most part, just have to open up the drive, and check for DC voltage. Here on this side, I need a scope, like we have sitting here. And using a scope, basically, when you get into some real fine test requirements, this is my portable scope that I use for testing motors. So basically, how does it work? First stage is the converter section. There's what we call a 6-pulse drive, because each one of these diodes puts out a pulse. So A phase, I've got a positive pulse, and I'm taking this negative sine wave and turning it into a positive pulse. And then B phase comes along, 120 degrees later, starts doing the same thing. So my DC bus sees this coming in. And then along comes the capacitor, and its capacitor fills in these hollow spots to smooth this out to where it looks like a flat line. Any questions? Understandable? And down here at the bottom, the peak on a 40-volt bus is 679 volts. I think that's what we ran as far as calculations go. And develops the voltage needed for the DC bus. And then the capacitor comes along, and boom. Downstream of the capacitor is our DC bus, 650 volts DC, and it looks like that. The input looks like this, goes to the diodes, puts out this ripple effect, and this is on the positive side. There is no negative here. These are all positive ripples. Zero line would be right below that. There's nothing down here. So here we go with this ripple, hits the capacitor, and puts out a flat line. DC signal that enters the engine section. And the engine section starts putting out this 6-pulse signal, and it's going to actually have 6 steps to it. As it goes up, our sine wave goes up, it's going to go up 3 times and down. 1, 2, 3, 1, 2, 3. 3 steps up, 3 steps down, 6 pulse. And that's what it looks like. And there's where the dirty power comes from, because it's not a smooth sinusoidal waveform. And that's what you're seeing here. Kind of hard to see, but there's 3 steps to the top and 3 steps to the bottom. Then we go to the negative side to develop the other half of the sine wave that the motor wants to see. So that's why bonding the motor becomes so critical. So basically, we take, in order to slow the motor down, we slow the frequency, but in the process, we have to lower the voltage. So as I go to 30, from 60 hertz to 30 hertz, I start out at 480, therefore my voltage, my frequency drops in half, my voltage drops in half. But my DC bus is still 650 volts. Now if I drop to 10 hertz, so I'm 1/3 of 30, my voltage is 1/3 of 240. So it's all pretty linear. So I'm not only controlling the frequency of the hertz, I'm also, in the same time, I'm controlling the voltage to that motor. The problem we have with modulated signals is remember, this is 600 volts DC or 650 on drive. Problem is, the leading edge of these pulses is somewhere around 900 volts DC. Why is that? Inrush to motor, what, 6 to 10 times run load, right? So anytime you turn something on that's controlled by inductance, transformer, motor, that inrush, you actually hear it. When you turn a transformer on, you actually hear that inrush. So the inrush to these pulses, 900 volts. Therefore, we cannot, should not use THHN wire because the insulation is so thin, those 900 volt pulses will poke holes through the insulation. And in fact, the ABB manual specifically states, do not use THHN wire. But believe it or not, a lot of people use it because it's thinner diameter, therefore I can use a smaller conduit. So the whole price starts to drop when I go to THHN wire. Not thinking of the end results. Any questions? So, the signal to the drive, signal from the drive to the motor is a square wave, basically. There's a square wave. And when we switch the frequency, we have to likewise change the voltage to match the drop in frequency. Pulse width modulated signal. That's pretty much how a drive operates. It's simply a pulse. More ons, less offs, the faster the motor spins. More offs, less ons, the slower the motor spins. So, the biggest problem we have with VFD drive motors is bearing failures. I just have so many bearings. This one here is beautiful, this big guy. This came from UNR. The race of the bearing is electronic manufacturing, electronic discharge manufacturing.
How long do these last before they get back?
Is that,
How long do they go before they get back?
depends on how bad it's wired. The motor, the worst I've seen is 6 months. And that's because that's the one where I got shocked when I got on top of the air handler, because nothing was grounded. The beauty of that one is, that big one came off the UNR. That big one that you passed around there, they changed the bearings on the motor. But when a bearing goes bad like that, it puts out a very high-pitched noise that's really hard on the ears. Change those bearings on the motor, and the sound in the air handler room was still screaming. They had to change the bearings on the fan. The fan. So, how do I get those pulses from the motor that's being generated from the motor to the fan to damage those fan bearings? The belt is a conducting surface. So remember, it's going to travel in any path it can to get to ground. So if my motor's not properly bonded, that discharge voltage is going to look for every source it can to get to ground. Right? Because in order to get back home to the source, I'm going to find every path I can. Because my drive is grounded, the motor is grounded, the fan is grounded, and all these discharges are heading out here on the belt, gets the fan bearing, heads to ground, so all these guys are coming back to ground in every path possible. So, without taking proper mitigation methods, they'll continue to replace those bearings because this is never going to stop unless I fix the problem that's causing those discharge voltages. Where's they coming from? They're coming from the drive. That's what starts them. The 10,000 hertz signal from that drive to spin that motor is bleeding through the stator of the motor to the rotor, because the rotor is attached to the shaft. The shaft is attached to some grounded means, because my motor's not bonded, my motor's simply grounded so I don't get shocked. So it's a high impedance path for high frequency. Building grounds are a high impedance path. To high frequency, it's an open circuit. So, my metal parts are a much lower impedance path to get back to the drive than the NEC ground that grounds the motor. Because the motor is grounded for personal protection, not for high frequency.
So,
right?
Carl, you fix that by bonding the motors and putting filters in?
Say again?
Do you fix that by bonding the motors and putting filters in?
Yes. Absolutely. In fact, my first encounter with this was out at Summit Racing. I told the contractor out there, here's your problem, The fix is bond this motor. The temperature on the motor dropped 40 degrees after you bonded the motor. That's all you do is bond the motor. I ran across a new device while I was working at the hospital in Dallas. I'm sure you've probably heard of these. You've seen on these maybe power supplies to your computer, this little nodule that's on the cord, feeding low voltage to your computer. These ferrule modules, which are pretty much here, eliminate the EMI, high frequency, that's on that cable. That signal, that 10,000 hertz signal, generates EMI, RFI and EMI. And it well, what's a capacitor? It's two conductors with an insulator. So my wire going to my motor is just nothing but a gigantic capacitor. And that high frequency can couple through that wire and therefore causes EMI and RFI, depending on the frequency. Remember, RFI is below 15 kilohertz. EMI is above 15 kilohertz. So they developed this product. This sucks up that energy. So these are putting on the output of the drives now to suck up that high frequency.
Does it store that energy or does it just dissipate it?
What's that?
Does it store all that frequency or does it just dissipate it?
Dissipates. Yeah. I had never seen them before, knew nothing about them, but they had these boxes of these that they're going to put on the drives because they kept losing motor bearings. I actually seen it on that hospital in Dallas on the chiller, the brand new chiller that had been brought to the project. And in that chiller were those devices. The chiller had a variable speed drive on it. Carrier chiller had a variable speed drive on it. The output of that chiller had those on it. And whoa, the carrier thinks that much of it, there must be something to it. So the hospital bought a bunch of them, they're going to put them in the output of their drives. So I said, well, let's test it. So I put my meter on. This guy right here, I can put on the shaft of the motor, and I can read the discharge voltage coming off that motor. So it's a very good, unique tool now for me to diagnose motors before they take out the bearings. So we take, before they put those on, they hadn't bonded the motor. I says, you know, we've got to get these motors bonded. So let's test one. So then they had ABB drives. So went out there, put on one motor. We were getting about 3.5 volts discharging off the shaft of that motor. So they bonded the motor, and the voltage dropped about just a little bit less than 2. I said, okay, let's put those guys on and see what happens. It dropped to less than 1. I said, oh, there must be something to it. So I bought me a kit, and I want to put one on my goal is to put one of these on a solar inverter that I'm losing, as you saw, that I'm losing wire, AC contactors, AC disconnects, fuse holders. It's melting this stuff. And it has to be, in my opinion, the high frequency of the engine, the IGBTs, converting DC to AC. Because I don't know what else it is. So I'm going to try one of these and see if it can dissipate, because I saw with my scope that switching frequency on the DC bus. I saw it on the AC bus. I didn't think that it would that it would travel through to the DC bus, but it did, because the Sparks Police Station, when they converted their cars to Bluetooth connected computers and the equipment inside their cars, when they park underneath the parking structure, it was all lined with solar panels, their Bluetooth equipment went berserk. So wow. So I put a filter on the DC bus and the AC bus to filter out that EMI that was traveling through on the DC side of the system. Well, the DC side of the system is where I'm losing all of this. All this melting is happening on both the AC and the DC side. And you'll see when we get that section here, the damage that can occur to our electrical equipment. And it's amazing how much destruction is going on in the PV world. Where's my water? Any questions? So, basically, are VFD so great after all? In my opinion, if you don't install them properly and do the mitigation measures necessary, the energy you save is going to be just enough money to maintain that equipment, because you're going to destroy it. So you might as well take all that saved money, put it in this pot so I can give it to my maintenance staff to rebuild, right? And that's kind of what's happening. We save a bunch of money for energy, it looks good to the power company, but they better put that money away so they can rebuild all the equipment that it's destroying. So, we improve efficiency, but we keep breaking things down. Either the drive's going to go, the motor bearing is certainly going to go, and you're going to burn out windings and transformers, and you're going to burn out windings and motors. And there we go. Always keep control conductors away from power conductors, because of the EMI generated by everything that's got a power supply in it. Because of the switch mode power supplies and everything that's got electronics attached to it. And that switch mode power supply puts out RFI and EMI noise that's going to affect anything that's close to it. And if you have an opportunity to drive next to a 900 kW inverter, put your radio station on an AM station and see how close you can get to that inverter before you have to turn your radio off, because of all the EMI and RFI coming off that inverter. Probably 50 feet is about close you can get to those inverters. And you have to turn your radio off. So you can only imagine what it must look like if you could see it. And there we go. GHHN wire. Insulation breakdown. And that rapid change of voltage, dVdt. Delta voltage, delta time. The amount of voltage change and the amount of time that it's occurring in. That's what dVdt stands for. Delta voltage, delta time. And it will break insulation down, causing heat, melting insulation. So here we get the skin effect. How many have heard of skin effect? What is your interpretation of skin effect?
Is it the heat or energy loss caused by flow of electrons on the surface of a conductor?
Correct. So, I learned about it when I was in apprentice school. They talked about skin effect. But then it was high voltage. And when I worked on a nuclear power plant, the copper coming off the 25 kV generator was hollow copper tube, 4-foot diameter hollow copper tube, because of the skin effect, due to high voltage traveling on the surface area of the conduit, of the conductor. So that means, why do I need solid copper if I'm only going to use the outside surface? So the higher the voltage and the higher the frequency now, the thinner that copper gets. So, therefore, building wire sucks for grounding purposes because we're dealing with high frequency. And if we're dealing with high frequency, a building wire becomes an open circuit or a high impedance path to provide a path for high frequency, ground faults, anything that travels at high frequency, which coming off a drive is exactly where we're in. So basically what it's saying is the amount of copper at 10 kilohertz uses like 24% of the copper. The higher the frequency, pretty soon the higher frequency, you're only using 1% of the copper. So I just got to provide more copper. And I can't do that with building wire because it only comes with either 7 or 11 strands. So therefore I have to use LDO cable, locomotive cable or battery cable, which has probably 200 and plus strands in it. Well, sure, there's tiny strands, but if I'm only using a small component of the strand, I don't need a big thick piece of wire. I need just a whole lot of little tiny ones, right? More paths for high frequency to travel on. So locomotive cable, LDO, is a perfect use for grounding variable speed drives motors, providing a equipotential ground path for grounding your electric rooms. Now, we talk about the 7th harmonic. A harmonic is simply a multiplier of the fundamental being 60 hertz. So, the first harmonic is 60 hertz, the fundamental. The second harmonic, double that. The third harmonic, triple that, right? So the third harmonic, 180, the fifth, 300, the seventh, on and on and on. Drives put out primarily 5th and 7th harmonics. That's the majority of harmonics coming off of drives. There's a lot of others, but they're in smaller magnitude, but generates 5th and 7th. So the 7th harmonic increases 64%. You've increased the impedance of that conductor 64% at the 7th harmonic. So that's why building wire does not work as a low impedance path for bleeding high speed frequencies off of drives. Because drive is going to have a lot higher than 7th. It's going to have 15th and 21st all the way up to 50 hertz. 50 harmonic, the 50th harmonic. What's 50 times 60? Well, you got 2 zeros there and a 30. That's 3,000 hertz. That's what's being generated by a drive, right? So you can only imagine how thin that wire gets now. It's like it ain't even there. The skin depth is inversely proportional to the square root of the frequency. The third harmonic, the 5th harmonic, the square of the 5th harmonic. So, this is what a discharge looks like. Electronic discharge machining. That is a method used by manufacturing to cut metal. This happened to be that fan that I was working on that I got up on top of. I was trying to find a grounding surface to provide a grounding means to my scope and got zapped. 58 volts discharging off that motor, on, through the bearings, onto the shaft of that motor, trying to get back to its source. They were gonna change the bearings on that motor. I already set a bearing sitting there. Oh, we're getting ready to change the bearings. When I walked in the mechanic room, oh my gosh, it was screaming so loud, it was hurting my ears. He said, oh, no, we're gonna change those bearings. I says, don't bother changing the bearings, because they're gonna go out in another 6 months. So when I showed him this, I says, you gotta fix the problem, because if you don't fix that problem, the set of bearings you're gonna put in there, you're gonna be doing it again another 6 months, and another 6 months. Because it can't go away unless you fix the problem.
So how'd you guys fix the problem there, Carl?
What's that?
How'd you guys fix the problem there? Is that, how'd you fix the problem?
Grounding,
Grounding.
bonding and grounding. Proper grounding and, of course, proper bonding. Because you can bond a motor, but if the motor's not grounded, you haven't really done anything. So here's that bearing that just passed around. Common mode noise. Common mode is voltage ground, voltage neutral, voltage ground, because you don't have a neutral for the most part in the motor.
So you said right there, if you bonded it, but you didn't ground it, you didn't really do anything? What if you grounded it, but didn't really bond it? Would it be the same result?
Well, you do ground it just in your basic electrical installation. You ground it, and for the most part, when you pull a wire into the peckerhead, you got a little screw there, and you wrap the wire around this screw, and you put your cap back on, and you're done. Okay, oh great, I ain't gonna get shot, gonna touch that sucker. But that's it. I've done nothing for the problem that's causing these bearings to get zapped by those electric discharges. So, the industry right now is using these brushes that's being put out there because it's an easy fix. There's a company that makes these and sells them by the ton, and they're even selling motors with these already on the motors. And I put this Band-Aid on there, and that's okay. It's a Band-Aid. What do you mean? I said, well, how long are the brushes gonna last? If that motor's spinning 24/7, and those brushes are riding on that shaft, how long is that? How long before those little fibers don't work no more? And then the next thing you know, you burn out a bearing. Oh, I guess I gotta replace that. I guess I gotta replace that again. I said, why don't you fix the problem? So everybody got a Band-Aid for everything we got in our industry right now. It's like pulling separate neutrals to our phase conductor. 200% neutrals in our panels. Duh. Why do we fix the problem? Just fix the problem. Because I asked you, did anybody pull round robins anymore? And nobody's even heard of them. Pulling one neutral with 3 phase conductors, A, B, C, and neutral. Because in the real world, the neutral is going to carry hardly no current. The neutral pulled by the power company into your service is going to be half the size of the phase conductors. They know there's going to be no current on that neutral conductor. Why don't we? How come we don't? Our fix is to pull separate neutral. Well, that raises the price of the project. Well, why don't we just get rid of the problem? We go back to pulling round robins? I don't know. So, as you can see, that braided strap, and you can buy them in separate lengths, and this outfit in Dallas at the hospital put these braided straps on if I go out to check it out. They got them bolted onto a painted surface. How much resistance do you suppose that painted surface has? Well, you know, paint's a resistor. I said, sand the paint off. You're trying to provide a low impedance path. You land it on a painted surface, an insulator, you haven't accomplished anything. You know, you have to do this so that it works. So, sand the paint off, and you bolt this to the pad. Pad sitting on a concrete surface. Concrete's an insulator. So I said, if you bond the motor, but it ain't grounded, you've accomplished nothing. Therefore, I have to take this pad to a effective ground, which means I gotta use LDO cable, not building wire, because I'm trying to drain high frequency off that motor so that I don't go through the bearings into the shaft. Because remember, it's all starting on the stator, which is attached to the frame, the solid part of the motor. I don't want to capacitively couple it into the rotor because that's my path to ground, right? That shaft is connected to a grounded surface. And if I'm generating all this high frequency up here in this part, I'm going to go through that bearing into the shaft because that's my path to ground. But if I provide this now, there's my low impedance path to ground, only if that pad is grounded properly, effectively. Now, I fixed that problem. I don't have to change bearings no more. I don't have to put that Band-Aid brush on there. There's a fix. And believe it or not, it come out again, EC&M, Electrical Construction Maintenance. And that came out in 2018. Wow. What are we, 2025 now? Ooh, 7 years ago. Holy smokes. And we still don't do it. Because nobody reads this magazine, I guess. Don't ground your motors. Instead, ensure the motor installation is properly bonded. It didn't say bonded, it says properly bonded. Because again, if I do it like that and I don't ground it, I have not done it in a proper method. That make sense? See how easy that was? So, more specs and application for VFDs. Shielded cable. Have any of you seen a VFD cable?
Right over here.
Have any of you seen VFD cable? You probably never will because it's very costly.
I think I saw one on a transformer.
Anyway, it looks like that. It's got a separate conductor, a separate ground wire for each conductor, and each conductor's got a shield around it. That shield is to capture that high frequency. The ground wire is to drain that so that it don't get to the motor. But the chances of you ever putting it in, slim to none. Because it's very costly. So, what's my alternative to that?
Use aluminum.
Well, you already seen them. We can put filters on the drive, and we can bond the motor. We can have a decent, effective ground system, and we won't have to pull up to the motor. Because if I put a filter on the output of the drive, I don't have that high frequency generated down the wire to the motor and then feeding back to the drive because of the high frequency bouncing off the impedance of the motor and heading back to drive. So a high frequency going to the motor, hits the motor, bounces off the motor, and heads back to drive. So smokes the motor, smokes the drive. So the fix is in place. Filter the output, bond the motor, and properly ground the structure of the motor. That ground has to get back to the source. The source being the drive to the switchboard to the main. One continuous path all the way to the main. Because any break in the middle of that is going to create a problem. lot of this stuff I pulled out of the ABB manuals. Shaft grounding, insulated bearings, different sources, different methods of preventing the motor shaft bearings problems that we experienced. So, research has shown VFDs operate at higher carrier frequencies, leading to a higher rate of current discharge pulses and bearing damage. And it's been going on for a lot of years. And it'll continue to go on until we do this work properly. And lightning strikes we're dealing with here, coming in off the grid. So without proper surge suppression, which we covered earlier, utility capacitor switching creates transients on the grid, and all those events coming in from the grid can cause the grid power quality issues, which is now starting to affect LED lighting, which is the most sensitive component of our system now. Most drives can ride through these faults, but LED lighting can't. And IT room, all the sensitive electronic equipment. This is a nice, easy test that you can conduct. I call it a pulse point. My goal here is to determine between my neutral and my ground bus, if my neutral and ground bus are tied together somewhere in the building, I'm going to have voltage on my ground conductor. For instance, if the the generator is bonded, neutral ground bonded, and I got a 3-pole ATS, I'm going to have voltage on between the neutral and the ground. I don't want more than a volt. I want something greater than 0, because if it's 0, that means they're both tied together. And there's no difference of potential. If I try to measure voltage across a piece of wire, I'm going to measure 0 because there's no difference of potential. So I measure 0 on that pulse point, which is in a panel. What's the voltage reading between ground and neutral? And we're going to go downstairs to the solar room where there's a ground rod driven. We're going to measure that ground rod, and then we're going to disconnect it, and you can read the voltage between that conductor and the ground rod. So let's take a break, and then when we reassemble, we'll go down there and we'll play some games with that brand new ground rod they drove down there. Because our goal is, okay, moving onward before we fire up this equipment over here. We've only got a few more slides left here. And this particular slide is the Reno Sparks water treatment plant had an arc fault. I'd gotten called out earlier to do some load testing because they kept blowing the fuses on the pole. They were 15 amp fuses, but 15 amps don't sound like a lot, but 25 kVA times 15 amps, that is a lot of power. So the power company went in, raised it to 20 amp fuses, and they kept blowing the 20 amp fuses. So they were blaming the water treatment plant using too much power. So I had my power quality meter on the main switchboard and had me monitoring it, and they had a ground fault on the power pole right outside the plant. And a 25 kV ground fault is amazing. It's like sticks of dynamite going off. It's like a bomb went off right outside. It was in the daytime too, but the light that was generated was so bright, the maintenance guy's inside the main electric room, and the pole's probably from this window to about where the end of the parking lot is. But it was so bright, it lit up this electric room just through the door. Well, I haven't had my meter on, so I downloaded the data. So what you're looking at here is, now this is kilovolts. So there's 2,500 volts, 2.4 kilovolts, right? So that's the main power. And the amps is on the different phases, and this is in milliseconds. So one cycle is 16 milliseconds. So this particular chart's running 160 milliseconds from here to here. So that arc flash happened right in here. And so that's that's probably 8 milliseconds right there because of the half a cycle. And it generated so much energy, it was incredible. So here's where the cutouts blew because we lost power. Voltage went from 2.4 kV down to 0. The amps, when that happened, went to almost 3,000 amps at that instant. And this is 14 seconds from here to here. So that arc flash happened right in that time frame. And C phase, A phase and C phase generated 2.1, 2.6 thousand amps. Well, the power company was blaming the utility was blaming power company. Nelson Electric was the contractor, and they asked me if I would, they wanted to check out the pole. Well, Nelson Electric didn't want to get on a bucket truck and go up there and check a 25 kV line to see what was going on, so they asked me to fly my drone. So I flew my drone around this pole and identified the problem, and here's where it occurred. It started right here. This is C phase, that's B phase. So it started here at C phase, and it blew this away, and you'll see that in another image. But you can see that this ground wire for the surge trap is bare copper. It's insulated here, but turns to bare copper where this fuse holder is. If you got 25 kV within probably 2 or 3 inches of that copper wire. That'd be a very rainy day, so the pole got pretty wet. So it provided enough conductivity that it just blew this, went to ground right here, and it blew the whole thing apart, and it just blew, I mean, it blew everything apart. But I flew my drone around that pole with all these images, and the power company realized it was their fault because they didn't have that ground wire grounded next to that arc flash guy. And one of my jobs was also check for issues with terminations. I thought I had this tool in my truck, but I didn't. I was going to bring it in. This guy here is an ultrasonic tester. And because this is a 4160 board, I didn't want to be opening anything up to check for looseness. But this ultrasonic tester, as you can see, the lights start to light. It's at about the number 5 light. And I'm just measuring noise from loose terminations outside the switchboard. So this is an awesome tool for checking loose terminations. Non-invasive. And if you got breakers that are tripping, nuisance breaker trippings, great test for that, because when contacts get dirty and pitted, they'll buzz. They'll buzz at 60 hertz. And we call it microscopic arcs and sparks that happen inside those contacts. And that puts out ultrasonic sound. And so I use that to test for loose termination before they generate heat and create a problem. Just a nice test tool to carry around in your ditty bag. This is the frequency, this is on an inverter, solar inverter. This is the frequency generated by the engine, the IGBTs that create the AC, converting DC to AC. And when I break that down into smaller components, I can count the little variations in that sine wave, and it works out to be 10,000 hertz. That's 21 milliseconds, so if we start at 0, there's just one sine wave, just short of the second sine wave, because 16 milliseconds is one sine wave. So that shows me the noise coming off, which is EMI and RFI generated noise that creates havoc to microprocessors. And in this case, like the Sparks police station, it's creating problems underneath the carport, which created problems to their Bluetooth connected equipment. Generated enough EMI that inside the car, it was creating havoc. And my solution was to put a filter on the inverter to filter out this equipment. Well, that same situation is happening with variable speed drives. They're doing the same thing, converting AC to DC. Same time you do that conversion with IGBTs, switching in high frequency, it generates that kind of a sine wave. This is current, and this is voltage up here. And you can kind of see that voltage sine wave is kind of fuzzy. It's not a solid line. So that fuzzy voltage sine wave is feeding equipment connected to, because it's a common grid, so everything connected to it sees that fuzzy sine wave. We call it waves because it's so small, but affects small electronic equipment. Anything that's got a program, it'll cause issues with programming equipment. So this is that power pole. You can see C phase, this guy over here, here's B phase. A phase stayed in place, but because the arc flash started over here and flew this away, it blew this guy out. But they had generated, the energy had dissipated enough that it didn't blow this guy out. That was pretty interesting because the resolution of the camera, the bolt that's attached to this guy right there, as you can see, that energy came to this way and it melted the threads on that thread. So I could see the direction of the arc flash just because it melted the threads off that bolt and they stayed intact on that side. So you can kind of see the direction that arc traveled. So that kind of, and you can see the copper wire burned off, and you can see a black trace along that wooden arm right there. But so the power company had to rebuild that whole pole for them. But anyway, our next class will be dealing with harmonics.